Here's the lecture for section 5.3, having to do with conditional probabilities and independence. And that is definitely going to be the big theme here. We're going to have to define what a conditional probability is, and then we'll learn how to use conditional probabilities when making tree diagrams, and we'll define independent events. And we'll have some new um, probability rules that we'll work on. Um, it says the probability we assign to event can change if we know some other event has happened. And this idea is heavily embedded into a bunch of the stuff that we'll be doing in the near future. So we have this thing called uh, a conditional probability. The probability that one event's happen given that another event is already known to happen is called a conditional probability. Our symbol here is P for probability, event B, given that event A has happened. So this little vertical line, given that, or under the condition that. Let's see this in play on this problem. So students at the University of New Harmony received 10,000 course grades last semester. The 2A table breaks down these grades by the school of the university. And then the schools are the liberal arts school, the engineering school, and the health and human services school. Um, they have what kind of grades are given? Were they an A, B, or below a B? And let's say we have some events defined. Event E is that it comes from an EPS course, meaning it's coming from this engineering physical sciences school. And event L is that the score is lower than a B. Let's talk about probability of L. Probability of L. This is probability that the grade is low. Well, there were 3,656 low grades given out of the total 10,000 grades given. All right. And what does that mean in context? Well, that proportion is about 36.5%. So we could say about 36.5% of all grades given were below B. And here's our context. Now let's take a look at two of these conditional probabilities. This first one reads, what's the probability of the grade coming from the EPS school given that it's low? Now, when we do this kind of calculation, we basically say given that it's low means that we are restricted to only the low grades, and we pretend like the rest of the table doesn't exist. So we might say that the probability that the grade comes from EPS, given that it's low, is the 800 scores from the EPS school divided by the 3,656 number of grades that were low, and that ends up being 0.2188. The other ask they ask is, what's the probability that it's a low grade given that it's from the EPS school? Now, in this case, maybe I should switch to a blue marker, means that we're only looking at this particular row for this probability. In this particular row, the low scores are 800 out of the 1600, and that's 0.5. Now it asks, which of these conditional probabilities tells you whether the college EPS schools tend to score lower than the other groups? And the answer is the second one, because this is the one that says um, amongst EPS students, uh, approximately 50% had low scores or low grades. Okay, so this is the one that looks exclusively at EPS and tells us within that group we got a low grade. And when you compare that score, the number of what percentage were low grades as compared to um, the low scores generally in the college, you can see, yeah, amongst that school, grades are pretty low. Let's go on and let's get a even more firm definition. Oh, sorry. Let's use the conditional probability to find this new, very important idea called independence. When knowledge of one event has happened does not change the likelihood of the other event, we say that the two events are independent. That is, if two events A and B are independent, it means that the occurrence of one event has no effect on the chance of the other event. In other words, the conditional probability of A given B is the same as just the probability of A, or the conditional probability of B given A is just the same as the probability of B. Let's take a look at this. Is there a relationship between gender and handedness? Um, to find out, we looked at some data of 50 Australian high school students. Two-way table gives the gender in the dominant hand. Um, Are the events male and left-handed independent? Well, let's ask the question, what's the probability, at least according to this table, that a randomly selected person is male? Well, that means it looks like there's 23 out of 50, and that's 46%. Now, let's give you more information. What's the probability that they're male given that they're left-handed? Well, in that case, I'm only looking at the left-handedness or the handedness, and we'll say, well, among the left-handed people, 3 out of 7 or 0.4286, 42.86% are male. Um, Strictly speaking, for right now, since the probability of male does not equal the probability of male given left-handedness, we say that these two events are not independent. Later on, we'll do some more um, critical analysis of this, but for right now, let's let that be our rule. All right? Check for understanding. Are these events independent? Shuffle a standard deck of cards and turn over the top card. Place it back into the deck, shuffle again, and turn over the top card. To find events A, first card is a heart. Event B, second card is a heart. Well, um, I classify these events to be independent because by replacing and shuffling the first card drawn, the probability of getting a heart has not changed. So independent. Let's take a look at second one. Shuffle a standard deck of cards. Turn over the first two cards one at a time. To find events A, first card is a heart, and event B, second card is a heart. These two events are not independent. And let's talk about why. Um, if the first card is a heart, then the probability probability the second card is a heart is lower. And I could say the same thing again. Basically, if the first card is not a heart, the probability of the second card being a heart goes up. So in other words, regardless of the outcome of the first one, the second probability changes. All right. Number three, the 28 students in Mr. Tabor's AP Statistics class completed a brief survey. One of the questions asked whether the students was right or left-handed. To a table summarizes the class data. Choose a student from the class at random. The events of interest are female and right-handed. Well, in this case, let's say what the probability of being female is. And that would be, I'm going to have to fill out some stuff here. 21, 7 for those totals. And over here we have some more totals, and that will be what? 4 and 24. In both ways, they add up to 28. So the probability of being a female is 21 out of 28, which ends up being 0.75. The probability of being a female, given that you are right-handed, and again, I'm just going to highlight the right-handed row to signify that we're only working within that row. Well, that would be 18 out of 24, which ends up being 0.75 as well. And so therefore, because the probability of being female and the probability of being female, given that you're right-handed, is the same, that means the two events are independent. All right. Tree diagrams. One of the most useful tools in dealing with probability questions is the tree diagram. Let's consider flipping a coin twice. Let's build a tree diagram from there. So we always start at the beginning. That's a very good place to start. And we think about the first event and how that event may turn out. Well, if you flip a coin, you could get a head or you could get a tail. Now we're on to the second coin flip. After the first coin flip happens, you can get a head or a tail, or a head or a tail. And this allows us to specify the sample space. Head, head is a possible outcome. Head, tail is a possible outcome. Tail, head is an outcome, and tail, tail is an outcome. Now, since each one of these events is equally likely, we simply would say, well, the probability of head-head would have to be 0.25. Each of these has probability 0.25. But another way of looking at this problem is to say, hey, when I did my first coin flip, there was a 50% chance that I got a head or a 50% chance I got a tail. And the same thing happens on every single one of these routes. And if we think about this particular item in our sample space, you can actually see that 0.5 times 0.5 gives us that 0.25. Now, this one's a situation where all items are equally likely, but let's talk about another one that's a little bit more complicated. Um, let's say we choose two students, one at a time, from this class, and I think we're going to do something having to do with left-handed. So we're going to be looking at handedness as we make a two-way table. Handedness. Okay. Um, choose our first student. Well, they could either be left-handed or right-handed. Now, what's the probability on that first draw. Again, let me put my numbers in here, total of 28. What's the probability that they're left-handed? Well, there are four left-handed students out of the 28, and there are 24 right-hand students out of the 28. Now, I'm going to choose a second student. But now there are, if if the first student was left-handed, there's one less left-handed student to choose from. There's only three, and there's only 27 of the students to choose from. And likewise, there are still 24 right-handed students, but there's only 27 of them um, to choose from. Left-handed, right-handed. If the first student chosen was a right-handed student, then there is 20, I'm sorry, there's 4 out of 23 that are left-handed, or 23 out of 20, sorry, that should be an 8 out of 28 there. So there's our two-way table. Find the probability that both students are left-handed. Well, probability of the first one being left and the second one being left-handed ends up being 4/28 times 3/27. And I'm just going to go to Desmos and do that calculation real quickly. Let's go over here. 4/28 plus 3/27. Oh, there should be a plus there. There should be a multiplication. Let's multiply them. And I get the probability of getting two left-handed kids is about 0.159. 0.159, right? But you can see how this diagram helps lead us to that answer. Let's do something maybe a little bit more complicated. Um, First of all, let's just talk about what we just did can be codified in the idea is that we have something called the general multiplication rule, all right? And it was embedded in the kind of tree diagram thing that we just did. Imagine event A, and this is the probability of A. If we go on to event B, this isn't the probability of P, this is the probability of B, given that A has happened. Probability of A times the probability of B given that A has happened is exactly what we're doing on that tree diagram. So for example, the Pew Internet and American Life Project finds that 93% of teenagers use the internet and 55% of them have posted a profile on a social networking site. Question, what percent of teens online have posted a profile? This is asking what's the probability of teens and having a I don't know, let's call it S for social networking. We can think of this as being the probability of being a teen times the probability of doing social networking given that you're a teen. Okay? Sorry, not probability of being a teen. Sorry, probability of being online. Online, on the internet. I for internet. Okay? Probability of a teen being on the internet in that when the survey was made was 93%. And then amongst the online teens, that'd be amongst those that are online, 55% were um, uh, were doing social networking. And again, if we put those numbers in, 0.93 times 0.55, we get 51.15%, 0.1515 there. All right. Now, again, if it's helpful, you could have thought of that as being online versus not being online. And 93% of teens are online. Social networking was 55% of the online teens. If we wanted to pull this off, we could say, well, that's 45 for the people who are not on social networking. Among the teens that are not online, 0% have social networking and 100% are not social networking. So you could see how the rest of that table would look. All right, let's go on to the next page. Let's take a look at some more uh, diagrams. Um, Video sharing sites led by YouTube are popular destinations on the internet. Let's look at adult internet users 18 and over. About 27% of the internet users are 18 to 29s. Another 45% are 30 to 49s, and the remaining of them are old, like me, 50 and over. Um, the Pew Internet Life Project finds that 70% of the internet users that are at age have gone to video sharing sites. So let's say start taking a look at what this tree diagram could look like. First of all, we got our different age groups: 18 to 29, 30 to 49, and 50 plus. And we basically said that this was 27%, this is 45%, and this is 28%. Now, amongst those, you could either be a video yes or a video no. And the video yes, so 70% of the young people are using video sharing sites. So I can go ahead and put those two branches of the table up there. There's video yes again. And here's video no again. And for the middle-aged people, it says 51%. So 0.15 and its complement 0.49. And then of the older people, it says 26% are video yes. And that means 74% are video no's. And there's our table. But we want to find out the unconditional probability of video yes. How might we do that? Well, the probability of video yes, let me make this a little bit bigger, could be thought of as the sum of the, I'll call them the event y, young, and yes, plus let's call these people the middle age people, probability of middle and yes. And let's call these people the olds, plus the probability of being old and yes. Or can I calculate these? Well, if I multiply 0.27 times 0.7, the probability of being young and being a video yes is 0.27 times 0.7, which ends up being 18.9. I did those calculations earlier. Probability of being middle-aged and a video yes, well, that's going to be 0.45 times 0.51. That ends up being about 0.2295. And then lastly, the probability of being old and a video yes ends up being 0.28 times 0.26. And again, I did this calculation earlier. It ends up being 1.1, or sorry, 0.0728. So if we add up those numbers, showing my work all the way through, I end up getting 0.4913. What's my conclusion? My conclusion is about 49.13% of all adults use video sharing sites. All righty, going to the next page. A computer company makes desktop and laptop computers at factories in three states, California, Texas, and New York. The California factory produces 40% of the company's computers. The Texas factory makes 25%, and the remaining 35% are manufactured in New York. Of the computers made in California, 75% are laptops. Of those made in Texas and New York, 70 and 50% respectively are laptops. All computers are first shipped to a distribution center in Missouri before being sent out to the stores. Suppose we select a computer at random from the distribution center. So let's make a tree diagram for this situation. Well, we have California, we've got Texas, and we've got New York. And the probability that a computer is made in California is 0.4, 0.25 for Texas, and for New York, 0.35. Now, it could be a laptop or it could be a desktop. And according to our narrative, 75% are laptops, which means that 25% are desktops. Laptop for Texas, 0.7. That means 0.30% for desktops. And for New York, half are laptops, half are desktops. Now, suppose we select a computer at random from the distribution. What's the probability that the computer is a laptop? Well, we can calculate the probability of California and laptop. And I'll write it out this one just for which is the probability that it's from California and the probability it's a laptop given that it's from California. 0.4 times 0.75. I do that calculation ahead of time, and that is 0.28. Probability of being from Texas and being a laptop, that's 0.25 times 0.7, which ends up being 0.245. That number doesn't look quite right. Let me double check that. 0.25 times 0.7. Okay, indeed that number is wrong. That was 189, right? And then the probability that it's from New York and is a laptop is 0.35 times 0.5, and that should be 17.5. All right? So what's the probability of it being a laptop? Well, the probability that the computer is a laptop will be the probability that it's a California laptop plus the probability that it's a New York laptop plus the probability of it being, sorry, this is supposed to be a Texas laptop. And this last one is a New York laptop, which is 0.280 plus 1.89 plus 1 or 7, 1 or 0.189, 0.175. 9 plus 5 is a 4. Carry the 1, 9, 17, 24. Carry the 2, 2, 4, 5, 6. So it looks like about 64.4% are laptops. All right, move on to another idea. If two events are independent, then the probability of A and B can be thought of as the probability of A times the probability of B. This is the same idea that the probability of A and B is the probability of A times the probability of B given A. But since we know that B given A is equal to the probability of just B, just like it says there, that means this thing can get replaced with this probability of B. And that's the special multiplication rule for independent events. Very important stuff. Um, on January 28th, 1986, the Space Shuttle Challenger exploded on takeoff. All seven crew members were killed. Following the disaster, scientists and statisticians helped analyze what went wrong. They determined that the failure of O-ring joints in the shuttle's booster rockets were to blame. Under the cold conditions that day, experts estimate the probability that an individual O-ring would function properly was 97.7%. But there were six of these O-rings, and all six had to function properly for the shuttle to launch safely. Assuming that they succeed or fail independently, find the probability that it would safely launch. All right. So the probability can be thought of as a 97.7% that the first O-ring did fine, and another 97.7% that the second O-ring went fine. And you can see that I would just get a chain of these. And when I finally got to here, the probability of all six doing fine ends up being 0.977 to the sixth power. Now, what number is that? 0.977 to the sixth power. It ends up being 86.97%. All right. Our conclusion, the shuttle had a 86.97% chance, not change, chance of launching properly. Okay. Now, please note, and this is going to be reinforced again, that means the probability of at least one O-ring failure was 1 minus this 8697, which ends up being 13.03%. Okay, so this at least one can always be thought of as 1 minus the probability that nothing bad happened, or none. There were no things that were wrong. That's a really high probability of failure, and it was a really, really sad day. So this idea of at least one has some really, really strange effects. The first trimester screen is a non-invasive test given in the first trimester of pregnancy to determine if there are specific chromosomal abnormalities in the fetus. According to a study published in the New York Journal of Medicine in November 2005, approximately 5% of normal pregnancies will receive a positive test. Let me make that clear, that even though everything is fine, 5%, they'll say positive that there is an abnormality. Among 100 people, 100 women with normal pregnancy, what is the probability there'll be at least one false positive? Now, again, the probability calculation here is that a single test being not positive is 0.95. So we can say, well, what's the probability that all 100 had negative results? Well, the probability of 100 negative results is 0.95 to the 100th power. And this is surprisingly 0.0059. Less than 1% of the time, they'll get 100 negative results, meaning 100 women all saying baby's normal when the baby really is normal. So what's the probability then of at least one false positive? Well, it's 1 minus the probability of all negatives. or 1 minus 0.0059, which ends up being 0.9941. A huge probability that there's going to be at least one false negative, or sorry, false positive. All right. So, how do we end up calculating conditional probabilities? Well, we already know from looking at the tree diagram, event A, event B, again, this is probability A, this is probability of B given A, that this gives us the probability of A and B. Well, if we start here with that known formula, and if we divide by the probability of A, then we get the conditional probability formula of that probability of B given A is equal to the probability of A and B divided by the probability of A. And that formula we're going to use right now. It says we classified 100 households having to do with their phone uses. What's the probability the random selected household has a landline with a landline, also has a cell phone? Probability that they have a cell phone given that they have a landline. See how it says amongst those with landlines. Well, the probability of a cell phone given that they have a landline is the probability of having a cell phone and a landline divided by the probability of having a landline. Well, the probability of having a cell phone and a landline, that's right there. It's 0.6. Probability of having a landline is 0.78. Doing that math, it ends up being 76.92. So you can see how we're using this formula to calculate that conditional probability. But you can also see how when we did other conditional probabilities, it's doing exactly what we did. Isolate the condition and then do your calculations only within that one line. Um, Sometimes we use conditional probabilities to work backward. We had that example about the internet adult users and whether they use video sharing sites or not. Here's that complete tree diagram all done out. But this time we're going to ask a different question. What percent of the adult users who use video sharing sites are aged 18 to 29? Note, this number here is not that answer. This is the answer. What's the probability that they are a video yes, given that they are within the young age range? This question is reading, what's the probability that they're young, given that we know that they share video? So how are we going to do this calculation? Well, the probability of being young, given that you're a yes, well, that would have to be the probability of being young and video sharing divided by the probability of video sharing. Now, the probability of video sharing, now, first of all, this one's easy to calculate. It's right here, 0.1890. But the yeses are in these three groups. So the yeses are 0.189 plus 0.2295 plus 0.078. And if we go and put that into the calculator, we end up getting 0.3847. So again, the idea is here's a randomly selected person. I tell you that they share video, and you say, well, there's about a 38% chance, a 38% chance that they're young. Now, So with that calculation, um, about 38 point, let me change it to a percentage. About 38.47% who share a video site are young. Compare this to the probability that 27% in general adults share it. See how different those numbers are? That suggests that whether you share video and what age you are not independent. All right. That happens to be our last example. We learned a lot, but really big concepts about conditional probability and independence, some new formulas, and that concludes not only section 5.3, but it concludes all the lectures for chapter 5.